Discovery's 4 computers now have primary control of critical vehicle functions.
All right, everyone, welcome to today's ASRG webinar. But before we get started, I'd like to tell you a little bit about ASRG and get some of the legal stuff out of the way. ASRG is a nonprofit organization founded to support the development of the automotive security industry. We have developed a platform and a community to share knowledge, communicate through networks, and to build value with collaboration. This is a community for you, built by you, with the goal to protect our friends and family when using automotive products. If you want to learn more about ASRG or get more involved, please visit our website at www.asrg.io or send us an email at hello@asrg.io. Before we jump into the presentation today, let's get some of the legal stuff taken care of. The views and opinions expressed in this webinar are the views of those that have made them. They do not represent views or opinions of ASRG and are to be considered as informational. The use of this information is to be used by the individual and/or organization at their own risk.
My name is Dr. Ken Tindell. I am the CTO of Canis Labs. In this talk, I'm going to explain the concept of CAN protocol attacks, demonstrating them in the lab. Before we discuss CAN protocol attacks, let's talk about the opposite, frame attacks. Frame attacks use a CAN controller and play by the rules of CAN, or at least the rules that the hardware enforces. Frame attacks on the CAN bus are classic attacks, for example spoofing, where a frame is sent as if from another device, or bus flooding, where a storm of frames slows the bus down. CAN protocol attacks are different. They're attacks on the CAN protocol itself. They work by software directly accessing a CAN transceiver's pins and can drive an arbitrary signal onto the bus. This means there are no rules. The software can do anything to drive the behavior of other CAN controllers on the bus. This talk is going to demonstrate 5 different CAN protocol attacks. These attacks are especially important because they can be combined together to achieve higher level attacks. A CAN protocol attack works like this. Software takes away control of the TX and RX pins that go to the CAN transceiver and switches them to being general purpose I/O or GPIO pins. This is done in nearly all microcontrollers with an internal logic block called a pin mux. Once the pins are repurposed as GPIO, the value of the TX output pin can be set and the value of the RX pin read. Malware that hijacks a device can bitbang these pins to run a crude emulation of the CAN protocol. The software doesn't follow all the rules of CAN, just enough to drive other CAN controllers to behave in certain ways. Canis Labs has produced the open source CANHack toolkit, written in Portable Embedded C, and baked it into MicroPython firmware on the Raspberry Pi Pico. And you can make a CANHack board just by wiring up a CAN transceiver to a pair of I/O pins on a Raspberry Pi Pico. Now let's go to the lab and see our demonstration kit, and see how to send a CAN frame in pure software using the CANHack toolkit. Here is the benchtop demonstration kit. This is a Raspberry Pi 4. This is a logic analyzer connected via USB to the Raspberry Pi. This is a CANHack board and a Raspberry Pi Pico connected to the Canis Labs CANPico board. And here's another CANPico board. And the Canis Labs CANHack board has RX and TX pins from the transceiver connected through to the logic analyzer. This is the Raspberry Pi desktop, and we can start by opening up a window onto the CANHack board, and we can create an instance of the CANHack toolkit, and we can set the details of the CAN frame that we want to send. So that's a 5-byte CAN frame, and we can get ready to send it, but we need to be able to see it. So what we'll do is we'll open up a logic analyzer, and this is the pulse view logic analyzer from the Sigrok project, and it's got the CAN RX and TX lines defined and a falling edge trigger for the CAN RX line. and it's running the CAN2 protocol decoder that will show us details of the CAN frame that it sees. So if we arm the trigger, we send the frame, here is the resulting frame. So it's the ID of 123 and contains the 5-byte payload, hello. And it's also given us here a little warning that this is an ACK error it's spotted, because this bit is not set to 0. And that's because there's nothing else on the bus to set it to 0. If this were a CAN controller, it would retransmit the frame in a continuous loop. But because it's a software implementation, we haven't programmed it to do that. What we could do, just to show it working, is actually create a CAN controller, set it up running on one of the CANPico boards, and do this again. There. Now we see here an extra signal on the RX line, and there's no ACK error because the CANPico board that sent the ACK bit, and it should have received the CAN frame. So we can see here it's a 5-byte CAN frame with a standard ID of 123, and that's our 5-byte payload. So we can see that just with software we can transmit a fake CAN frame on the CAN bus and get other devices to accept it as real. Now it's time to carry out a CAN protocol attack, the bus off attack. This was the first ever CAN protocol attack. It was first described by Cho and Shin at the University of Michigan in 2016. The attack destroys frames from a targeted controller. The goal is to increment the transmit error counter by 8 and do this 32 times. That will put the transmit error counter above 255. And then the targeted CAN controller goes bus off. When it's bus off, it cannot communicate, and recovery takes at least 3 milliseconds or up to 33 milliseconds on a busy bus. That's for a 500 kilobit per second bus. It's longer at slower bit rates. Let's go off to the lab and see the attack in practice. We can demonstrate the bus off attack using 2 CANPico boards, a sender and a receiver, and the CANHack board. So these are windows open on the MicroPython running on these 3 different boards. So on one of the boards here we create our CAN controller, and then we create an instance of the CANPico toolkit library that's just got some predefined functions that we can find useful. And one of those is called mon, and that just prints the CAN frames that it sees on the bus. It's basically a very simple bus monitor. On the other board, which is going to be the sender, we shall send a couple of different CAN frames. So let's create an instance of our CAN controller, and let's create a couple of CAN frames. So the first CAN frame will have an ID of 100 and a payload, hello. And the second CAN frame will have a CAN ID of, let's say, 123 and a payload of world. So we're going to send 2 different CAN frames. Now what we're going to do is attack CAN frame 2. So the way we'll do that is to create an instance of our CANHack toolkit, and we will set the CAN ID that we want to attack, which is going to be 123. And the way we'll do it is with the error attack function. And what we'll do is that generates an error when it sees a particular ID, but we want to repeat the error to push the transmitter into a bus off state. And each error increments the transmit error counter by 8, and 32 increments of that will drive it above the threshold for bus off, and the CAN control, the sender, will be forced bus off. So what we'll do is we'll send these 2 frames on F2, and we'll use the logic analyzer, which triggers on a falling edge of CAN RX and has our CAN2 protocol decoder in it, So we'll trigger that, start the attack, and send those frames. So the frame with ID 100 has been received, and that was sent, no problem. And you can see the end of frame and then the transmitted OK event. But when 123 was sent, the CANHack attack took place. And the way that works is it generates an error frame. Here has been flagged up, so you can see the error frame started here, and then it was flagged up by this decoder as an error. That causes the other controllers to go into an error, and then there's a period of superposition where all the error flags collide with each other, and then this is the error delimiter, and in the CAN error recovery protocol this stands in place for the normal end of frame. Now normally after the error delimiter you would see the interframe space and the next frame would begin, but we generate another error here, and another error, and another error, and a long sequence of these error frames. There we go. And then we have interframe space at the end, but there's nothing to send. And the reason there's nothing to send, despite the transmitter failing, is the transmitter went bus off. Now if we bring up the status of that controller, it's actually showing here a transmit error count of 0. And the reason is the microchip CAN controller automatically recovers from bus off in hardware. That's actually something that the CAN standard doesn't anticipate. Normally you'd expect software to detect bus off and then to ask the controller to recover, but the microchip hardware automatically recovers. But it's thrown away all of its pending frames because it effectively resets the CAN controller. So that's why we don't see the transmit error count above 0, and that's why we don't see the bus off status, because it's already recovered. So we can see the CANHack toolkit has targeted a specific frame ID. So frames that aren't that ID are allowed through and they're received, and frames with that specific ID are hit with 32 back-to-back error frames that force the transmitter offline. And that's the basic bus off attack. That's the bus off attack. Now let's look at spoofing. Spoofing is a classic CAN attack where we want to get devices to accept a fake frame. But the timing is crucial depending on the buffering of the receiver we want to fool. If the buffering software lets newer frames overwrite old ones, then the spoof needs to come after a real frame, so the application is likely to see the spoof. If the buffering software discards newer frames until the older frame is processed, then the spoof needs to come before a real frame. In either case, classic frame attack spoofing using a CAN controller risks the doom loop. The doom loop happens when two CAN controllers send the same frame at the same time and they clash, causing errors, and then both retransmit their frames. This happens again and again and again in a loop, and we can show this happening in the lab. To see what happens when two CAN controllers both transmit frames with the same ID, we can use the two CANPico boards. So what we have is a pair of sync frames. The first sync frame is just a simple short CAN frame with ID 0, no payload. And when the other side receives that frame, it queues its own CAN frame in through the drivers, and they would make their way through the driver software and eventually into the CAN controller. And then when arbitration starts, the CAN controller will enter that new frame into arbitration. But because that takes a little bit of time for the drivers to work, we have a second sync frame that keeps the bus busy with an 8-byte data frame, so that the drivers have got plenty of time to put the frame into the CAN controller, and the CAN controller can spot that that frame is ready to go. So that when the second sync frame is finished, arbitration starts, and both the sender at both sides are both putting into arbitration the same frame ID, but with different contents. So we can create a CAN frame on this side. With one payload. And we can create a CAN frame on the other side with the same ID, but a different payload. The CANPico library has a very simple little function that waits for a CAN frame and then queues a CAN frame. So we'll use that. It's called sync send frame, and we'll use that to send a frame once it's received a frame. So that's now waiting for a frame. So if we arm our logic analyzer, send the sync frames, then we get this. We can see here the two sync frames and the data for the second sync frame. So these are both sent as normal. And then here is ID 123. And this is where both the transmitters are trying to send the same frame ID and overwriting each other. And of course, one has a slightly different payload to another, so that will generate a bit error. And eventually that leads to error recovery and the superposition of all the error frames and the normal CAN error process. So here the logic analyzer decoder has seen a stuff error. Then we get the error frame, which is the error flag and the error delimiter, into frame space, start to frame. It starts sending 1, 2, 3 again, and on and on and on and on we go. So if we look, we see 16 of these errors. So we get to here. This is in basically a doom loop that takes us from no errors on our error counters to 128, which takes us both devices into error passive. At the end of this doom loop, one of the controllers will have transmitted a frame correctly and dropped from 128 to 127 on its transmit error counter, and that drops it out of error passive. The other controller is still left in error passive because its transmit error counter went higher for the last frame. And that's the doom loop at work. We just saw how spoofing can go wrong with the doom loop. We can avoid this with the error passive spoof attack. The properties of error passive can be exploited to carry out a spoofing attack, where the spoof should appear first and appear with the same timing as the original frame. The attack is a protocol attack, so there is no risk of a doom loop. It works by pushing the sender of the real frame into error passive. Then the software waits for the real frame to start being sent. When the software sees the frame ID, it starts overwriting the rest of the real frame with the rest of the spoof frame. Receivers see the spoof frame at exactly the same time as the real frame, but with the spoofed contents. The sender cannot signal an error and stop that frame because it's in error passive mode. Let's go back to the lab and see the error passive spoof attack carried out for real. To demonstrate an error passive spoof attack, we need our two CANPico boards and the CANHack board. So from the first Pico board we will use as a monitor, and we have our friendly CANPico library, and we'll just run the monitor program from that. So we define a CAN frame for it, and we'll target CAN frame with 1, 2, 3, and we'll have a payload of dead beef. Now we're going to attack this with the CANHack toolkit, and we're going to set the frame and we're going to set the payload to cafe food, like so. So the first thing to do is to attack it with the error attack, and we'll repeat this about 20 times, so that should push it into error passive. So if we send this frame, so we'll target the attack and send the frame. And now we can see it's gone error passive. Now we can mount the spoof attack. So that's set up to attack the targeted frame. So what we'll do is we'll run the logic analyzer, target the frame and send it. So we have transmitted our spoof frame first, and then the victim's frame comes second. And there are lots of techniques we could use to delay this second frame. We could kill it again, and there's other techniques. So we can spoof a targeted error passive node with an arbitrary overwrite of its payload with the payload we want to spoof. The next CAN protocol attack exploits a tiny flaw in the CAN protocol. Before we talk about that, we need to discuss a key property of the CAN protocol, something that is very useful and almost unique to CAN: atomic multicast. This is where a message is broadcast to the bus, and either everybody gets the message or no one does. It's a kind of consensus system. Everyone sees a consistent view of a message, but sometimes some receivers may get the message more than once. That's not the fault of CAN, it's actually a flaw in the universe itself. It's not possible to ever guarantee multiple observers see a consistent view of a changing value at the same time. Leslie Lamport, famous for the Byzantine generals problem, discovered this fundamental principle, which he calls Buridan's principle. It's well worth reading his paper on it, because it crops up in multiple places in computing and electronics. But back to the CAN protocol. For receivers, a frame is deemed complete at the second to last bit of the end of frame field. A receiver that sees an error in this bit will raise an error flag, overwriting the next bits, but receivers that don't see an error will accept the frame. For transmitters, a frame is deemed complete if the last bit of EOF is read as a 1. If the transmitter sees a 0, then it raises an error flag and does not mark its frame as sent. It will re-enter into arbitration to be sent again, and it will be received again. This means that some receivers will see the frame twice. This is obviously something that can be exploited by a CAN protocol attack. The target of attack is an event message. Multiple receipts of a state message, such as sensor readings, most likely don't have severe consequences. An example of an event message is a servo command to turn +5 degrees. Receiving this message twice will change its meaning by moving the servo a total of 10 degrees. And the attack can be repeated multiple times. Let's go back to the lab to see this attack for real. So to mount the double receive attack, we will have a CANPico board that is a receiver, a transmitter CANPico board, and a CANHack board to attack it. So on our receiver, we will use the CANPico library and just run a monitor that displays the frames it receives. And we will define a frame on the sending side that we're going to attack. Now let's pretend this is a servo command of some kind. So we will attack that frame. And we will mount, and we will tell it we want just one extra frame. So we can have a look at what's going to happen here with the logic analyzer. We'll get ready to send the frame. On the logic analyzer, mount the attack, send the frame, and have a look at what happens. So here is the frame being sent, and at the last bit of the end of frame we get an error frame which has been injected by the CANHack board, and that shows through on our logic analyzer as a double receive warning. So the frame is sent once, it's been received okay because that's the second to last EOF bit, but it's been failed to transmit okay, so the transmitter has resent it and it gets through, it's received okay again. And we can see in the monitor here that's been received twice, but it's only been sent once. We can also mount multiple attacks on this and send the frame more than just once extra. So we could send it, for example, 10 times. So if we get ready, arm the logic analyzer, mount the attack, send the frame, and look here. There's been a whole burst of these frames being attacked and resent. And here we have in total 11 extra receives of the frame. So if we wanted to send a servo command, the application is sending a servo command to move it by a certain number of degrees, and we wanted to magnify that movement by getting the software that sends this once. This receives it multiple times, and we can effectively take control of the servo through this double receive attack. The next attack exploits a mostly forgotten part of the CAN protocol. It silently freezes the bus for an arbitrary time. No CAN errors are generated by the attack, so it's mostly invisible to software. The only symptom is that frames are delayed. From a sender's perspective, frames are put into the CAN controller and they simply hang around in the controller for an arbitrary time. From a receiver's perspective, it's as if no one is sending frames and the bus is idle. This can have all kinds of effects. For example, depending on the CAN drivers, it can cause a frame to go missing when the next one is put into the buffer and overwrites it. Or a control loop is running fine, and then at a critical point, sensor readings don't turn up. Or a heartbeat frame doesn't turn up, and a crucial timeout's triggered. The protocol attack happens in the same part of the CAN frame as the double receive attack, around the EOF. A dominant bit in the first field of the interframe space has a special meaning. It signals an overload frame. The overload frame is a legacy feature of the CAN protocol, and it's not generated by modern CAN hardware. When CAN was invented, silicon was quite slow and ran with slow clock rates. Back then, it was quite difficult for hardware to move a frame into the buffer in time, so the protocol had overload frames added to allow a controller to ask for more time. You could say an overload frame is a kind of flow control for the hardware. Although controllers don't generate overload frames, they must accept them. The CAN specification defines rules on how often a controller is allowed to generate overload frames, but a CAN protocol attack doesn't need to obey the rules. Overload frames are identical to error frames, but with one big difference: they don't change the error counters. They won't drive a controller bus off or into error passive, and this means they're practically invisible to driver software. This lets us freeze all the controllers on the bus in a loop by sending one overload frame after another. When we stop, the controllers will unfreeze and continue as if nothing has happened. Let's go to the lab and see a freeze doom loop attack for real. The freeze doom loop attack could be illustrated with a CANPico A and B and CANHack. And on one of the boards, we will run the CANPico library monitor function. So that will just display the frames that it receives as it receives them. And over here, we've predefined a couple of frames to send. Frame 1 and frame 2. So frame 1 has a payload of hello, and frame 2 has a payload of world. And we're going to send a pair of frames, but we're going to attack the first frame with the freeze doom loop attack. So the first frame has an ID of 123, and we will run the freeze doom loop attack, and we will repeat the overload frames for 100 times, which is quite a long attack. So we open the logic analyzer, get ready to send the pair of frames. Frame 1 and frame 2, and we're going to attack the first one and add a load of overload frames in between. So arm the logic analyzer, mount the attack, send the frames. So we can see 2 frames have been received, but there's quite a gap between them. So the first frame goes here, and we can see it's been received okay. Then we get an overload frames all the way through, and then the next frame, world, hello world, is received okay. So that's why we see these two frames here. And if we look closer in, we can see what's going on. So in the first bit of the interframe space, the CANHack board has mounted an attack and put an error frame in here. That causes the error recovery process to go through. But with overload frames, that's not treated as an error. That's treated as overload. And we can see that by looking at the CAN controller, and the transmit error count is 0 because it's not counted as error. And we can add as many of these overload frames as we like to delay this. So here the delay has been about 3 milliseconds. So we've pulled out a huge chunk of bandwidth out of the CAN bus. That could be used for all kinds of attacks. So for example, we could force a timeout to happen because when we see a certain frame and another frame is expected in the application, we can force that second frame to be so delayed that it triggers a timeout and some kind of recovery process. Or we could combine it with other attacks to generate spoofs at particular times, and then delay the time that the sender tries to send its own valid frame to be passed any time the software would look at it. So this is extremely useful if you're an attacker, to freeze the bus at arbitrary points and trip up all kinds of application functionality. And we can even lock the bus out. We repeat this attack not for 100 times, but for 100,000 times. And we can mount the attack, send the frames, and the first one's been received and the attack is still going on, and now the second one has been received. So that's a delay right into human times of multiple seconds to mount an attack. So we could actually freeze the bus intermittently for as long as we like with this this freeze attack. So that's the freeze doom loop attack. Our next attack is a CAN protocol attack I discovered fairly recently, and I call it the Janus attack. It's named after the Roman god of field buses. No, the Roman god of religion and myth, sometimes called the two-faced god. This attack exploits the CAN rules for bit syncing. It causes different receivers to see different payloads for the same frame, a two-faced frame. The attack can be used to make a bad frame invisible to an intrusion detector or bus logger if it uses a regular CAN controller. It also breaks the atomic multicast property of CAN, so it would be possible to send different payloads and get different receivers to act differently. If they were instructed to move an actuator in different directions, then that could cause real physical world problems. To understand how the Janus attack works, we need to understand CAN bit sync rules. The CAN state machine samples bits using a time quantum clock, effectively polling the state of the line. A falling edge is used to synchronize a receiver to the start of a bit. If perfectly synced, the falling edge should occur in the sync seg part of the CAN bit. The sample is taken at a fixed time from the start of the bit. Values that change before this point do not affect the bit read. The Janus attack works by creating different values within a bit for different receivers to see. It's common to set a bus-wide sample point in specifications, but it's also common for programmers to just pick a 50% sample point when they don't know any better. The Janus attack exploits this difference. It works by pre-calculating two versions of a frame. There are some constraints on the two payloads. Firstly, version A and version B must have the same number of bits. Secondly, there are some constraints on the bit sequences within a payload. If the bits within a CAN bit are 1 then 0, then the next CAN bits must be 0 0 until a 1 1 CAN bit. It's straightforward to do a search for Janus compatible payloads, and there's actually some software in Python in the CANHack GitHub repository to do this. Let's go over to the lab and see the attack for real. So the Janus attack is going to attack two different receivers. Now we need to set up the CAN controllers slightly differently between them. So the first one will have a sample point of 75%, and the second one we'll set to 500 kilobits and 50%, which is a common default setting that lots of software and logic analyzers use. And then we will use the CANPico library monitor program to display what each of these devices sees. Then we will use CANHack, and we will set 2 frames. The first frame has the CAN ID of 123, and we will have a short payload of 10 hex. And then we'll set a second frame that is going to appear inside the same Janus frame with a slightly different payload, and we mark this as second frame. And we can actually see what those frames look like. So we see here the frames have the same number of bits. Now, to mount the attack, we need to use the logic analyzer to see what's happened, and we basically send the Janus frame. So if we arm the logic analyzer, send the Janus frame, here we go. So this receiver has received a hex 10 payload, and this receiver has received F4. So one frame was sent, and here it's marked as received OK. And the logic analyzer here sees, the decoder sees F4 as the payload, which is this 75%, which is what we set the sample point to. But the other device, because it's got a different sample point, sees a different payload. And we can see the bit stream here is not a regular CAN bit stream for this frame. So if we zoom in a little closer, we can see these strange bit formations here, which are not regular CAN bits. And that's the Canis bit. So this will read 0 in 1, and 1 in a second half, 0 and 1, 0 and 1. And they'll both receive a 1 here. All of them see zeros here, and so on. So we've managed to encode 2 different payloads inside the one frame by manipulating the CAN bit sync protocol, and by sending a carefully crafted sequence of 1s and 0s to the CAN TX pin, so that we can get 2 different receivers to see 2 different payloads. And that's basically the Janus attack. We've seen 5 different CAN protocol attacks in this talk, and they're really quite fiendish and do strange things to the hardware and the frames. I now want to cover what could be done to defend against them. Let's talk about detecting them. The first thing we can do is look for error frames. A lot of the attacks rely on generating error frames, and the patterns are unlikely to occur naturally. For example, a double receiving CAN is rare enough that few people have encountered it. It's quite Ian Fleming. Once is happenstance, twice is coincidence, 3 times is enemy action. This is why Canis Labs has developed its own intrusion detection silicon that counts double receive errors directly. Overload frames are invisible to most CAN controllers, but using the right hardware, they can be spotted. The Janus attack puts edges in a bit at unusual places. It can be detected by hardware that spots a pattern of rising or falling edges within a sequence of CAN bits. Protocol attacks that target a specific frame will normally wait until the frame ID has been seen, before generating errors. If the hardware can indicate what the ID was before the frame was destroyed, then this can be used to spot a pattern of errors that target a specific device. That's the kind of things we can do to detect CAN protocol attacks. Canis Labs has developed silicon to do just this, and much more. But detecting attacks is only one line of defense. We also want to frustrate CAN protocol attacks. Let's talk about ways to mitigate CAN protocol attacks. The attacks rely on malware having direct access to the transceiver. Well, we can easily stop that by using an external CAN controller. This isn't perfect, an external CAN controller costs more money than an internal one, but for some devices that are at high risk of being hijacked by malware, such as ones with huge amounts of complex software that's bound to contain vulnerabilities, this could be appropriate. Another approach is to use a security gateway. This keeps the malware far away from the transceiver. Now, security gateways have their own issues, such as dropping frames due to buffer overflows, so there are other considerations here. In any case, a device on the secure side of a gateway could still be hijacked. A quick way to make the Janus attack harder is to ensure the sample points are the same everywhere. And Canis Labs is currently developing a hardware test tool that can automatically check whether sample points are actually set. The double receive attack can be beaten by software if it includes a sequence number in frames and then discards frames that are retransmitted. This sequence number could be as small as a single bit that toggles. The error passive state is a key property that attacks can exploit. So one way to frustrate them is for software to recognize when the controller enters the error passive state and to reset it. This will need network management rules similar to those dealing with bus off, so that a hardware fault is detected and isolated. My final suggestion is to use Canis Labs Bus Guardian hardware on devices that are at risk of being hijacked by malware. The Bus Guardian is silicon that stands between the host CAN controller and the transceiver. It contains a CAN state machine, but also a protocol attack detector. This spots CAN protocol attacks, and that is one of the triggers for the Bus Guardian to disconnect the host from the CAN-TX pin of the transceiver. It also includes CANHD augmentation of CAN, where high-speed data bits are inserted into the spare time in a CAN frame. The Bus Guardian tags all outgoing CAN frames with a CANHD header that includes the hardware source address of the frame. An intrusion detection and prevention system, IDPS, can use this information to detect a frame attack trying to send a spoof. The Bus Guardian also accepts incoming commands from the IDPS to disconnect or reconnect the host. I hope you've enjoyed my talk on CAN protocol attacks. They may be fiendish attacks, but there are things we can do to frustrate them. If you want to know more about this area, then keep watching for some links to resources. All the demonstrations in this talk were done with open source hardware or software and can be downloaded from the CANHack repository.